Okay, chapters 1 through 3 review. Compare a statistic to a parameter. A statistic, okay, so a statistic, let me get my pen going here. It represents an attribute associated with a sample. For example, the sample mean, the sample standard deviation, sample variance. Whereas a parameter, that is associated with a population. The population mean, the population variance, the population standard deviation. So, for example, if I say the sample mean is 35, then 35 is a statistic. If I say the population standard deviation is 2.7, then 2.7 is a parameter. Number 2. Compare the difference between discrete data and continuous data. Well, discrete data is data that it has gaps between the outcomes. Okay, they say they're countable. For example, 1, 2, 3. All those numbers have gaps between them. So just kind of think of it in those terms. Whereas continuous data, think of continuous data as being data that is on an interval. That is, the population can be any number on a given interval of data. For example, the interval 0, 1. There are no gaps between any two numbers. Because you pick any two numbers, there's a number in between them. Okay? So discrete, think in terms of whole numbers, for example. Gaps, 1, 2, 3. Continuous, interval data. For the following data associated with a sample, calculate the mean and the standard deviation. We are given the actual data here. Now, later on, you're going to have a different type of calculation for the mean and standard deviation. But when you are given the actual data, the mean, you add up the data values. Okay, so you add them up. You divide by how many pieces of data you have. We have 5 pieces of data. That average is equal to 85. That's a 10 here. 85 over 5, which is 17. The standard deviation. When you're given the actual data, my suggestion is to form a table. The first column will consist of the data. So we're going to have 20, 30, 10, 15, and 10. Okay, so I'm going to have a table. Then I'm going to subtract the mean. Subtract the mean. I need a longer column than that, huh? Okay, so I'm doing this with a pen. So 20 minus 17, 3. 30 minus 17, 13. 10 minus 17, minus 7. 15 minus 17, minus 2. 10 minus 17, minus 7. After we subtract the mean, we're going to square. So what you should have memorized basically is list the data, subtract the mean, square it, right? When you square, it's always positive. 9, 13, I'm sorry, I gotta focus here, huh? I'm squaring it, yeah, I'm okay. 9, 13 squared, 169. Minus 7 squared, 49. Negative 2 squared, 4. Negative 7 squared, 49. Once again, notice everything in this column is positive. You are going to add up these numbers here. When you add these numbers up, you're going to get 200. Yeah. You're going to get 280. Then you're going to divide this by, is it going to be 5 or 4? Which one is it, 5 or 4? That's the big question mark. This is coming from a sample. Since it's coming from a sample, we subtract 1, so we're going to be dividing by 4. When you get that number, okay, 280 divided by 4, you get 70. But if you want the standard deviation, which is going to be S for a sample, this square root of 70. And then depending on how many places or they want you to round, I'm going to leave it like this. But again, take your square root of 70, then you can find your answer. It should come out to be, well, I'm going to do it here, 8.37. All right? Might be asked around one place or two places, but there you go. So standard deviation, list the data, subtract the mean, square it. Add that column up. The question is, if it's from a sample, you're going to be divided by the sample size less 1, which would be 4. If this were a population, meaning we had all the data, I'd be divided by 5. Moving on. All right, here's a question. What 2 rules might be used to find the percentage of data in a given interval centered at the mean? If you remember, way back when we're associating the percentage of data to an interval centered at the mean, it's possibly Chebyshev's. Okay, so Chebyshev's. Or the empirical rule. Okay? Chebyshev's or the empirical rule. What you want to keep in mind is one formula, and that formula relates the distance from the mean to an endpoint. Okay? You got 2 endpoints, right? That distance from the mean to an endpoint D is associated with the standard deviation, and that is D is equal to K times sigma. Now the value for K is going to be one of 2 things. If you're working with Chebyshev's, the percentage is at least 1 minus 1 over K squared. If you're working with the empirical rule, it's going to be from a table. K, percentage, when K is 1, 68%. When K is 2, 95%. When K is 3, 99.7%. So, depending on what K is, there's the associated percentage. 68, 95, 99.7. For Chebyshev's, we have a formula. The percentage is at least 1 minus 1 over K squared. So typically you're given the interval. You're going to have to find K from this formula. Then based upon if it's Chebyshev's or the empirical rule, you're going to either use a table or the formula. Now which one? The empirical rule is associated with bell-shaped data, right? So you'd have to see that word in the problem in order to use the empirical rule. Okay, let's look at this problem here. You should be reading it, trying to work it out. I'm going to point out some key information. That's the one thing you have to do during the final exams, is identify the problem. Right off, I am associating the percentage of data with an interval. Okay? Now, if this problem said something about normal distribution, this would be a Chapter 6 problem. It says nothing about a normal distribution, but it is about the percentage of data between 2 numbers. That's going to either be Chevyshev's or the empirical rule. Which one? Well, it's telling us this keyword here that the data is bell-shaped, so it's going to be the empirical rule. But no matter which one it actually is, we would get started in the same fashion. We have to determine the distance to an endpoint. So 297 over here, the distance from here to here is equal to 27. So our distance is 27, and we know that's related to the standard deviation by k times the standard deviation, which is 9. So k is equal to 3. When we look at the table, I'm not going to put it here, but for one standard deviation, it's 68. For 2 standard deviations, it's 95. For 3 standard deviations, the amount of data in this interval here is approximately 99.7%. There's your answer. Okay, stop the video and try working the problems. Or the problem, I should say, right? Okay, once again, identify the problem. We're talking about the percentage of data in a given interval. The problem says nothing about normal distribution, because if it did, we would be working with the z-table. So this has to be between Chevyshev's and the empirical rule. Nothing about bell-shaped data is stated in the problem. So this is Chevyshev's. Okay? So we are going to be working with the Chevyshev's formula. But again, since we have the interval, our first step is to determine the distance from the mean to an endpoint. That distance is 240. That distance is related to the standard deviations by k times the standard deviation, which is 120. When I divide, we find k is equal to 2. Now, this is not an empirical rule, so our percentage is going to be at least 1 minus 1 over k squared. Plug in 2 into the problem, 1 minus 1 over 4, which is 3/4, or about, or you can say at least 75%. So it's going to be at least 75% of all the population will be between 610 and 1090. Problem number 7. Once again, stop the video, try the problem. Identify the following histograms as either being right skewed, left skewed, I think there's an E missing here, whatever, bell-shaped, or uniform. I'm not an English instructor. All right, so right, left, bell-shaped, or uniform. All right, since the tail, we have a tail here, and it's on the left-hand side, that is left skewed. If you look at B, we have a tail, a single tail to the right side. This is right skewed. For C, if you kind of draw a line, it is almost a straight line. When you have a horizontal line, or it's very close to being a horizontal line, we call that uniform. And here's the one we all should be familiar with. If I kind of draw a line over these rectangles, It sort of looks like a hill to me. They call it bell-shaped. And that is what it is, bell-shaped. So, left tail, left skewed. Right tail, right skewed. About a horizontal line, uniform. Looks like a hill, looks like a bell. Problem number 8. The following histogram is based on a recent math test where test scores were grouped in classes and the number of test scores in a particular class was recorded. So you take a look at this histogram. I think it's a pretty histogram myself. But anyway, we need to answer the following questions. How many students scored between 50 and 59? Now, if you remember, in some books, like our book, there's not supposed to be any gaps between the classes, right? Okay, so the lower number actually is the start of the next class. So if we want 50 to 59, all of them actually are going to be in this particular interval. Even though this says 60 here, the 60 is really associated with the next rectangle. All right, so keep that in mind because they don't want any gaps between the classes, right? So this really consists of all test scores between 50 and 59, okay? So, 15, there you go. The height of this rectangle is about 15. The height of the rectangle represents the frequency. How many test scores were part of the survey? The number of test scores part of the survey, you would add up each one of these frequencies, right? If you add up all of these frequencies here, you should get 152. If you don't, either you are wrong or I am wrong. This video is unedited. You use it at your own risk. I hope I don't have any mistakes, but you let me know if you think I do, okay? And I'll check. But anyway, it's unedited. What is the relative frequency of test scores in the third class? So we look at the third class right here. 1, 2, 3. The frequency is 12. The total number of data values is 152. When you divide 12 by 152, you should get about 7.9%. So about 7.9% is the relative frequency. Remember, frequency is how many. Relative frequency is the proportion with respect to the total number of data values collected, right? So I think this is the end of this particular worksheet. Good luck with it. Practice, practice, and practice, right?